Alright, so this is lecture 23 on the second derivative test, and so here we're focused mostly on function of, two variables, and so the context is a function of two variables, like f of x, y, and we're considering a critical point. And what's a critical point? Well, a critical point, let's say x naught, y naught, is one for which the gradient of f, right, at the point x naught, y naught is just equal to 0, 0, right? So essentially what we learned is that in that context, f of x, y is equal to the function at the point, right? Plus, well, what ordinarily we'd have that, the first derivative terms, but those are 0. And so the next thing up is the, well, what we could call the Hessian, right? Q of, well, you could write it as Q of x. I could write this x as x naught, y minus y naught, and then plus higher order stuff, right? But this, if I expand it, is the formula is fxx, fxy, fxy, fyy times x minus x naught, y minus y naught over here, and the row vector, oh man, I made that. Poor planning on my part. So that's the formula for Q, and like that, right? So given a critical point, then the question is, like, is this largest or smallest? And so in the notes, I'll go through the notes here in a second, but I wanted to give an alternate linear algebra based argument here just for a second before I get into the notes. All right, and so just suppose for me for a second that you've had linear algebra and you know what eigenvalues and eigenvectors are, right? And maybe you don't at this point, maybe not, that's okay. You should learn sometime soon. And but anyway, long story short of it, what the linear algebra tells us here is that since this is a symmetric matrix, there exists something called Eigen Coordinates that you can rewrite this thing essentially as lambda 1 times, let's say, I'll say y. I don't need another letter here, so I'll just call it x bar squared plus lambda 2 y bar squared, right? And so here the lambda 1 and lambda 2 are called eigenvalues. They're eigenvalues, which means proper value or characteristic value, eigenvalues of that matrix over here. I'll call it A. So once you have that formula, it then becomes really easy to answer the question of, given a critical point, is it a max or a min? Well, certainly if both of these are positive, then it's going to be a minimum, right? Because anyway, anytime you go away from 0, 0, 0, so like here, anytime you go away from like 0, 0, this is going to get, larger than that value, right? And if both of the lambdas were negative, then that would be a maximum because you'd be taking away from that value with the Hessian term. If one of the eigenvalues is positive and one of them is negative, it's a saddle type thing because you could go up one direction, you go down another direction. And if one or both of the eigenvalues is 0, then we can't really say, all right? And so how do you find the eigenvalues of a 2 by 2 matrix? Well, for a 2 by 2 matrix, if you let me just use some easier letters here for a second, if we had A is equal to ABCD, right, then the determinant of A is equal to AD minus BC, right? But it's also equal to the product of the eigenvalues. That's one of the things linear algebra tells us. The determinant is the product of the eigenvalues. But another thing we know is that the trace of A, which in this case would be A plus D, is equal to the sum of the eigenvalues. All right? And so if you think about it, in this context, remember we just were saying that if they're both positive, it's a what? If they're both positive, it's a minimum, right? If they're both negative, it's a maximum, right? And so in that min or max case, the product of lambda 1 and lambda 2 would be positive, right? So this is going to be greater than 0 for min-max case. And on the other hand, lambda 1 plus lambda 2 equal to 0. Well, I don't know what I can say about that. I guess, oh, well, yeah. If they're both what? If they're both positive, this should be positive, right? If they're both negative, this should be I mean, so this is either going to be, so this is going to be like, for positive, it's going to be the minimum. And if this is negative, it's going to be the maximum case, right? And all right, and if the sign, if it's a saddle type, if one's positive and one's negative, then this determinant's going to be negative, right? But what is that determinant? Well, the determinant, and this is called the matrix of the quadratic form, the matrix of Q. This one right here, or I used A, I guess I can fine. I invented a letter, I might as well use it. Determinant of A. Well, that's equal to fxx, fyy, minus fxy squared. And for reasons I have no earthly idea why, but this is called big D in calculus books. And so essentially what I've described here is the fact that if D is positive, you know, well, one other thing, what's this trace of A equal to? A plus D, which would be fxx plus fyy. And if you think through it, the sign of the trace in the interesting cases, it's the same as the sign of either xx or the yy derivative. So, you know, basically you can just isolate and just look at xx. So, I don't know how to say this, but so anyway, this big D, if we check big D at a critical point, if it's positive, and if fxx is positive, it's going to be a local minimum. If this big D is positive and fxx is negative, then it's going to be a local maximum. And if we check big D and it's less than 0, then it's neither a local max nor a local min. And if big D is equal to 0, well then this analysis fails because the quadratic term doesn't dominate the series expansion. So anyway, that's a sort of a quick explanation for the second derivative test on the basis of you know, what's called the spectrum, the set of eigenvalues of the Hessian. Now the way I go about it in the notes is to fall back on that derivation I did earlier, where I used the method of Lagrange multipliers to find the maximum value and minimum value of a quadratic form on the circle. And so having done that, I then apply that result, right? So basically I did it for A, B, C quadratic form. Now I'm going to put A, B, and C equal to their corresponding expressions with the mixed partial derivatives, or partial derivatives, and identify basically that A is 1/2 x f(x), B is 1/2 xy, C is 1/2 fyy, and we plug that in to those gory results that I got in that previous section. You get, when you actually plug, that was my formula for the, you know, that lambda, the multiplier and the, you know, Lagrange multiplier analysis, you get this, which I then introduced the big D and broke down some cases. First of all, if D is less than 0, then this, the absolute value of that is, of course, equal to that, which is less than this. Which is to say that if d is less than 0, then the lambda plus and the lambda minus are going to have different signs. Lambda minus is negative, lambda plus is positive, and that means that the condition d less than 0 indicates a saddle shape for the graph. And likewise, if d is positive, then that means that the square root term dominates, and so, oh, excuse me, the other way around. The what? Huh. Well, I think I would say it the other way. I don't think that that dominates the sign of the solution. I think that the square root dominates the sign of the solution. Well, if fxx plus fyy is positive, then they're both positive. If fxx plus... Oh, okay, fine, yeah. Anyway, basically my point is you can go through this analysis piggybacked off that derivation I had in the previous part of the notes. And in any event, we get to the beloved, or the hated, or the often mysterious, because it's never explained, second derivative test. Because, you see, to really understand the second derivative test, goodness gracious, you need to talk about the multivariate Taylor expansion. If you haven't talked about the multivariate Taylor expansion, any proof that you'll find of the second derivative test, it's just, if you're really interested in understanding, you will not be happy. I just don't think you will. Anyway, we calculate big D at a critical point. Remember, so the terms and conditions here is we know that the first derivatives at that point are 0. We calculate second derivatives, put them together like so. If d is less than 0, it's not a local extreme. If d is positive and the x derivative is positive, it's a local min. If d is positive, the x derivative is negative, then it's a local max. All right, great. And then here's some examples. So calculate x squared. Zoom in a bit. X squared plus 2xy plus 2y squared. Calculate my gradient and set both of those equal to 0. That gives me the origin as a critical point. At least that's a critical point. And so I'm just going to focus our attention there. Second derivatives, 2, 4. So I calculate big D. Big D is 8 minus 4, which is equal to 4. And hey, look at that. That's a typo right there. What happened there is I have a left angle, so-called wrangle, rather than a greater than in my tech. I'll have to fix that. But I got rid of all those. Anyway, so it's positive, which means that min-max can be found. And since x derivative is positive, that means it is a local minimum. In other words, the graph z equals f of xy opens upward at the origin for that guy. All right. Next example. So again, the second derivative test allows us to decide whether a local, whether a critical point is the nature of the critical point, whether that local is a local min, a local max, or possibly neither. And again, there are examples where the second derivative test fails to apply, just like in Calculus 1. So we have minus x squared plus 2xy minus 2y squared. Calculate the gradient. Notice again that the origin is a critical point. So calculate my second derivatives, xx, xy, yy, minus 2, 2, and minus 4. So this one, these examples are kind of silly because we don't actually have to evaluate at the critical point because the second derivatives are constant, right? So like the evaluation's kind of stupid, but anyway, calculate my big D, it's positive, but this time xx is negative, therefore local maximum. That means z equals f of xy opens downward at the origin. And then another example, another origin's critical point. This time d is going to be negative, I'm guessing. Nope, d is 0, so the multivariate second derivative test fails. And we can easily see why this is the case, because in this case, f of xy, oh man, I'm sorry, I'm out of frame. My bad. Don't worry, you didn't miss much. So in this case, f of xy was what? It was x squared plus 2xy plus y squared. But if you tilt your head and squint, you can see that that's actually x plus y squared, right? So if you think about z equals to x plus y squared, it's going to be 0 along the line y equals minus x, right? So it's a parabola that opens up along the line y equals minus x. I could try to graph it, but maybe I have a picture here. Oh, in fact, I do. This picture right here shows you the previous 3 examples. So this one had the first example had a local minimum, the second one had a local maximum, and the third one is actually a parabolic trough. And it is subtle. I mean, that's the thing, is like, you know, 3-dimensional graphing, you may or may not be able to really see mins and maxes in your graphing. Like, man, unless you just zoom in just right, it could easily, the difference between a trough and an actual honest-to-goodness local max and min is fussy when you're just looking at them. So now this example is more interesting because it actually has the problem of evaluation in it. So here I've got this function. I calculate the critical points by calculating the gradient, putting it equal to 0. And in fact, when you work through the algebra there, you get a couple different points, I think. Let me see if I have them organized. I got 0, 0, and 2, 1 as critical points, right? Because I get either y equal to 0 or y equal to 1. So x is equal to 0 or 2 respectively. Okay, so anyway, if I could just read my own writing. Critical points of 0, 0 and 2, 1. Calculate the Hessian, right? Which is, this time, second derivative with respect to x gives me 6x, and then second derivative with respect to y gives me 4y from that 8y cubed term. And of course the xy term is still just constant, minus 12, but now the big D is a function of xy. See that? So it's that. And now if I plug in the critical points, I'll get different D's for different critical points, right? So I make a table of these things oftentimes. I think it's helpful. When you've got more than one critical point and things start to get complicated, it's helpful to make your answer a table. Please do that for my sake. 0, 0 is critical point. I calculate D is minus 144. I don't even need to calculate fxx. If once D is negative, we know it's a saddle. 2, 1, D is 432. fxx is actually 12. So that means f of 2, 1, which is equal to minus 8, is actually a local minimum. And so by the second derivative test, there's only one local extrema. And the local minimum value of minus 8 is attained at 2, 1. And I tell you what, folks, like if you try to look at it using a 3-dimensional plotter, it is hard to find, but it's in there. Oh man, I tell you what, these mins and maxes and functions of 2 variables, to see them visually, like okay, for a function of 1 variable, give me the graph, finds local mins and maxes. We can anybody can do that. You could teach that to middle schoolers without a problem, really. I think. But seeing mins and maxes for functions of 2 variables, looking at surfaces, trying to find like the top and the bottom of valleys of, you know, relatively wrinkly stuff, it's hard to see. Here's another one. So I have a function of 2 variables. I calculate the gradient to find the critical points, right? And I get this and that for x, y. I should set that equal to 0. That's a typo. And so from that I see we must have, to get fx equal to 0, we have three cases. Either x is equal to 1, y is equal to 0, or y is equal to 2, right? And if x is equal to 1, then basically I solve this one, and then once I've solved this one, then I see what does it force me to do over here, right? So if I put x equal to 1, that means this is 2, this is 1, and that means that this piece has to be 0. So if x is equal to 1, y has to be 1, right? So x equals 1, we require y equal to 1 to solve f of y equal to 0. That's the logic here, all right? If y equals to 0, that fixes this one, right? But then over here, we've got x times 2 minus x equal to 0. So we either need x equal to 0 or x equals to 2, right? 3, if y is equal to 2, we either need x equal to 0 or x equal to 2 again to solve that. So you put it all together, you got critical points 1, 1, 0, 0, 2, 0, 0, 2, and 2, 2. 1, 2, 3, 4, 5 critical points. This is exciting. And then you can calculate the Hessian. Excuse me. Well, I guess I'm calling this the Hessian now. But technically it's the derivative, it's the determinant of the Hessian matrix. But I guess this is also called the Hessian. I don't know, whatever. Stop this name calling. Anyway, so there's your big D. And it works out to that. And you can make a table, plug these things in. And you'll get D is positive in the 1, 1 critical point with an xx derivative, which is negative, which it tells you that f of 1, 1 is a local max. And on the other hand, the other 4 points give you negative Hessian, negative big D rather, and so it's a saddle at those points. And here's a picture of it. And you can kind of see, indeedly doodly, that there's just that one point there, which is a local maximum. And the other points apparently are saddles. So again, I mean, the structure of these examples is all the same. You have a function, you're trying to find local maxes and mins, so this thing you do to start with is you calculate the gradient, you set the gradient equal to 0, and that tells you, you know, what the critical point is. This one, you have an x and a y multiplying an exponential. The only way that can be 0 is, I'm sorry, I was out of frame. The only way that can be 0 is for both x and y to be 0. So in other words, the origin is the only critical point here. And so you can calculate second derivatives like so, and plug in 0, you get that minus 2, 0, and 2, and that means that the Hessian, or the big D, is negative, which means it's a saddle. Now, that's one way you could do this problem. There is another much easier way, right? Hopefully I do that next. Let's find out. So there's a picture. As you can see, it's kind of a saddle. It goes up this way, it goes down that way. Now my last, oh, here it is. Yay, I was hoping I would say this. So notice in the last example, it's easy to see why we found the result we did, because if you just use the exponential series, right, e to the theta equal 1 plus theta plus 1/2 theta squared, and so forth, with the substitution theta equal to minus x squared plus y squared, you can quickly derive that to quadratic order, the expansion is 1 plus y squared minus x squared. So I can actually look at that and tell you the eigenvalue is 1 and minus 1 for this. And as such, it's a saddle. You know, in other words, you got a plus squared, you got a minus squared. So if you hold x 0 and let y go larger than 0, it's going to increase. Whereas if I hold y equal to 0 and let x go non-zero, it's going to decrease from 1, and so it's a saddle. You can see all of that from this formula without going through all this fancy stuff. But anyway, either way you want to look at it. Here's another one just to illustrate the power series way of thinking again. We don't even have a second derivative test for 3 variables in this course because it requires linear algebra, and technically linear algebra is not required here. Anyway, so I mean, there is no second derivative test for 3 variables in the standard Calculus 3 course. It's too hard. Is the dominant groupthink in Calculus 3 educational circles. Anyway, so x squared plus y squared plus z squared minus 1/6, that cubed is what you get from plugging x squared plus y squared plus z squared into the power series for sine. And so there you go. Origin's a critical point, and the Hessian is actually x squared plus y squared plus z squared, from which I can immediately see that the origin is actually a local minimum. And yeah. So, yeah. And then here I describe, you know, this at the end of this, I basically, circling back to what I did at the start of this lecture, essentially, and just talking about the idea that for functions of more variables, we really need to look at the eigenvalues of the Hessian matrix, and the set of eigenvalues will determine the nature of the critical point. If all the eigenvalues are positive, it's a local min. If all of the eigenvalues are negative, it's a local max. If there's a mixture of positive and negative eigenvalues, it's a saddle. And if any of the eigenvalues are 0, we can't cipher the nature of the critical point from just the Hessian term. We need more. We need to look at third order at least data. But anyway, so that's about all I got here on this topic. And so next up is the closed set test, where we finally circle back and finish the discussion that we began with Lagrange multipliers. So thanks, guys.